Study.
Okay, so let's start.
Shall we start? Okay.
Okay, so hello everyone. Good morning, or maybe good afternoon, or good evening, depends on your time zone. I'm not sure, but I hope everyone stays safe and fine during this time. So, and thank you everyone for joining us today. So today we're going to talk about a statistical test, part two. Sounds like the second part of a movie, but it's a complement to the previous week, continuing with different tests. So as you will see in a minute. So I would like to start first with a brief introduction of myself. So my name is Kevin Pacheco-Barrios. I'm a physician from Peru and currently doing a postdoc research fellow at Neuromodulation Center. Actually, it's the Professor Fregni's lab, the same lab as him. And our main objective is to develop non-invasive interventions to modulate plasticity, especially in chronic pain and stroke and Parkinson's disease. So in all our activities, the statistic thinking is one of the most important ones. So today we're going to discuss using the same approach that we are using in the lab, as you will see, and we'll try to do more practical examples, like using this data, using some commands, using some coding. So I hope you're enjoying as well. This is my third year in PPCR, and so far it's a wonderful experience of learning and sharing ideas. So I hope you are also enjoying this program so far. Okay, so let's start. First of all, I don't have any conflict of interest related to this presentation. And then I would like to start with a warning from a neuroscience perspective, because potentially you will change your brain today, during and after this talking that we will have. Why? Because all the ideas that we plan to share between us will be decode from your sensory system and produce changes in your brain networks, in your temporal, in your frontal, and also subcortical areas. And these changes will generate some signals deep to your neurons, to your nucleus, and change the way that you are reading your DNA. So then you will produce new proteins. These proteins will go back to your membrane and start creating a new function, a new network. So at the end, we will share today, and in all these programs so far, collective neuroepigenetic change. So it's also to think like that. So this learning process and social interaction between us today will generate literally a new way of functioning in your brain. So my final remark on this is, please participate as much as you can in the forums, in all your optional lectures, your office hour, your general presentation as well, because as much as you intervene in this process, these plastic changes will be enhanced. So just keep in the back of your mind this idea. Okay, so this is the outline for today. We have three sections. The first one is a brief introduction about statistics. Then we'll go to discuss the case study number 10. And then we will move to categorical data analysis with some data examples, as you will see. Okay, so the introduction, really quick. So far you have different tools to start creating your house. I like this analogy because it's really like that. So you so far know how to state a research question, how to select your study population, your study design, and some methodological concepts like randomization, blinding, outcome selection, and also an important concept about ethics and integrity. So let's say that so far you can start building your house even for your future research, or to start assessing the house of other people in the papers, right? But in this process, to really finish your house, let's say, you need for sure the statistic thinking. So just remember, like it's a circle, so you need also the statistic to get your results, your interpretation, and then to restart thinking new questions. So it's really important to dominate as much as you can this concept of statistics. Okay, so when you start, I think 2 weeks ago or 3 weeks ago, start reading about statistics in the program, you know so far the types of data, the variable classification, continuous, categorical, and subtypes of these variables. Then also you know already the measurements of central tendency, right? The mean, median, and the measure of dispersion, like standard error or interquartile range, standard deviation. So you already know this idea. And also you know like this data, when you represent visually, you can identify some distributions, right? The distribution is just the visual assessment of your data. And you know that in statistics, we are obsessed, kind of obsessed with this special type of distribution, the normal distribution. Why? Because we can use this special visualization of the data to use it to calculate probabilities, right? Especially probabilities in the extremes of the distribution to start thinking on rare events, right? So then also you know that there are some theorems or some ideas that can help us to approximate to this ideal and sometimes utopic normal distribution. And then when you have this clear, you can state your hypothesis testing, right? Based on your null and your alternative hypothesis and choosing your threshold of significance and start selecting your test, right? So everyone is now in this moment, and you are thinking now selecting your test based on the variable that you have, the distribution that you found. So everyone is here now. So then you also need to understand that during this process of the analysis, you need always at least to represent these three pieces of information. The first one is your point estimate, right? Could be a mean difference, could be a proportion, could be a percentage of odds ratio, relative risk, as you already saw in some examples, right? But also together with this point estimate, it's really important to think on the interval measurement, right? Traditionally represented as a confidence interval using 95% of confidence, right? But it's important to have both always. And then the third piece of information is your p-value, right? And to report it as a continuous variable, not just categorical to say less or higher or more than 0.05, but also you need to represent the exact value to be more transparent, right? And then using these three pieces of information, you will start creating your own conclusion, your clinical and epidemiological interpretation, and to start having maybe a new idea for a new study if you are a researcher, or to start, I don't know, to make a better decision for your clinical practice, right? So that this framework is the same for categorical data, for continuous data, if you use parametric, non-parametric. So just keep in mind this idea that you need to interpret always your variables, your distribution, state your null, your alternative, right? Then based on this, select your test, create these three pieces of information, and ended up with your conclusion, right? So just as an introduction, because we will do this with categorical data today, as you will see. Okay, so let's start with a case. So please, Keiko, if you can help me to select one student to help me to summarize the PICOT of this case.
Yeah, from Japanese side, from Tokyo side, I think Satoshi-san, Kakugawa-sensei, can you take this opportunity to talk to this question?
Yes.
Okay, go ahead.
So Dr. Wang ran a trial to evaluate the effect of the exercise program for the treatment postpartum depression.
Mm-hmm.
And he showed the exercise group had significantly lower results after the treatment-based baseline as compared with the usual care group.
Great.
Yeah.
Yes. So yeah, it's perfect. Yes, a quick question. Do you think it's clear.
Sorry. Yeah.
If the T, which
T,
one will be the T? If you think it's clear in the case?
T is, I think, the 10-week. No?
Yeah, this is a good point. I mean, we can say that, but we don't know, right? Because this is the duration of the intervention, right?
Okay.
Because, but remember that this T is for all the study. So maybe if they have some follow-up, right? We need to include that time in this T. So yes, we can say 10 weeks, but it's not totally clear. Okay, but the others are perfect. Thank you so much. Okay,
thank you.
So as our colleague here explained us, we have this PICO framework, right? The postpartum depression woman, the exercise program versus usual care, right? And our main outcome is Hamilton rating scale, right? Like for depression. Let's say a scale for depression, right? And then the T, as I mentioned, it's not totally clear. We can say 10 weeks. It's not bad. But remember, like the idea include also potential follow-ups to be sure, like this is the T. So the next question for you will be, in this case, which one is the main dependent variable and the independent variable? Can you help me for that, Keiko, please? To ask to someone.
Of course. Okay. China side. Maybe Aurora, are you here?
Yes.
Okay, go ahead, please.
Sorry, I can't hear clear. Can you repeat your question?
Sure. Which one is the dependent variable in this case, and which one is the independent variable? The most important.
The independent variable is whether they take the exercise program, and the dependent variable is the different score they have accessed by the scale.
Great. Yes. That is really, you can see like it could be simple, right? But it's always important to start since the beginning thinking on which one is your dependent and your independent for what to state your null hypothesis, right? But it's perfect. Thank you so much. Okay. So then the next question will be, now you understand the idea of Professor Wang, you understand the independent and independent variables. So please, could you state which one will be your null or your alternative hypothesis? I saw a hand, Alberto, I think so.
Hello, can you hear me?
Yes.
Oh, okay, so I guess that the null hypothesis would be that there is no significant difference between the normal care and the new treatment, that in this case would be the exercise program. And the new hypothesis would be that there is an actual significant improvement in the outcome of the patients that follow this new program.
Great. Yes, perfect. That is the idea. As you can see here, I put an examples. Remember, like from the methodological perspective, is better, as you said, it's perfect, that no difference between groups, right? Or that there is a difference between groups. That is the idea. But from the statistical perspective, you can say like the difference between the improvement in the experimental group minus, right, the improvement in the control group is equal to 0. So this will be another way to state the same idea, just with numbers, right? Because if you improve in the experimental group 2 points, but also in the control group 2 points, at the end, you have 0 in the subtraction, meaning both groups are not different, right? Just remember that you can show in the 2 ways, but both are correct, okay? So perfect. So now we know the Picot question, the interventions, the variables, and then the hypothesis. So we are ready to understand the results and the process in the case study, right? So then what's happened with Professor Wang, right? He sent the paper to some journal, right? And he received some concerns from the reviewers. So someone can summarize what's happened with the reviewers?
Can I answer?
Sure. Go ahead.
Yeah, Dr. Wang sent his manuscript to American Journal of Obstetrician, and the journal committee replied by email that his manuscript is rejected, and they attach like a comment of reviewers. And when he read the comment, he realized that the main concern of reviewers that he used parametric test instead of despite his result is not normal distributed and his sample is small. So completely comment to this post or to these comments of reviewers' comments. If he complete if he reply to them in a good way, he may give him chance to review or to see to his manuscript or to revise his manuscript again, and this may or may not give him a chance to be accepted at that time.
Yeah, perfect. Yes, I think it's a common process. Maybe I don't know if most of you have kind of experience in the publication process, but yes, always this situation when you receive the reviewer's concern, always there is something that you need to fix. It's really, really rare like you receive a acceptance just really straightforward, right? I mean, so far in any of our publications we saw that, but yes, the main concern is the use of parametric tests when they kind of are suspicious, like the data is skewed, right? So the reviewers mainly say like why you use parametric tests in this case, and try to justify why. So okay, so then the question is, first you need to reflect on when we can use parametric tests, right? So we know that you have some assumptions, that you have some predefined characteristic that you need to fulfill before to use it. So let's summarize those. So I don't know if someone can help me to say this. Can you hear me? Keiko, please, if you can help me.
Hi.
Okay. Okay, go ahead. Fu?
I think the first one is the data. The data is just like continue data, and the data is abnormal distribution, and and the independent independent data or dependent data is also continue data, but not every. I don't say that. That's all. Sorry.
Yes. No, it's perfect. It's perfect. Yeah, you mentioned the most important characteristics. So mainly you need the assumption of normal distribution, and remember equal variance as well, right? So the dispersion between your groups should be not so different. You know, it's not possible to be exactly the same, but at least you expect not so departure from the variance difference. And then also it's more designed for continuous variables, right? Because you need this type of data. So okay, so what do you think happened with Professor Wang? Because he have independent measurements, right? Two groups. Apparently, also the depression scale is continuous, right? So which one do you think is the problem with him and these assumptions?
I think that is the analysis method, because the result of the clinical trial will be considered exploration, and then his data in this case is that nominee data, and the editors say they maybe use the non-parametric non-parametric test?
Yes, yes. So mainly, probably we don't know, we don't have the data to see, but probably it's because of the distribution is skewed, right? Because when he did the sampling, right, by chance, he got a lot of people with, I don't know, with mild depression. So you have in your curve of the depression data, you have more people in one side, right? So
Yeah.
that will be one explanation that why he experienced this problem, right? Okay, so perfect. So then this is a summary of the main, let's say, characteristic of parametric and non-parametric. As you know, the normal distribution assumption, the homogeneity of variance, right? So then there is another characteristic related to the strengths and weakness of both groups of tests, right? So one use the real data, the other could use surrogates like ranks, right? One, because the assumption is the normal distribution, so the sample size will be an important characteristic of your data to use parametric as well. And for sure, the non-parametric don't need this assumption and it's more robust for outliers, right? And then because you have more power in this parametric test using all the data, right? All the points in your data, in your observations, you can detect a small difference. But because you are using here ranks in the non-parametric, you could lose some detection power, right? And if you have a higher effect, for sure you will see it, but not as much as you can see with parametric, right? And then this is an important thing, and this is maybe why Dr. Wang also tend to use parametric, right? So why? Because if you use parametric, you can do a post-estimation changes, right? So adjustments, you can stratify, you can do a complex model, because let's say the plasticity post-estimation is better compared to the non-parametric, right? And then for sure, based on these post-estimation characteristics, you can use in complex designs, right? Not like in non-parametric that you are more restrict. Okay, so I think this is fine. So the next question for you will be, okay, so far you know some parametric tests, so please, you can give me some examples that you already know, just really quick.
Okay, probably Takeshi-san, Fujimoto-sensei. Let's try. Fujimoto-sensei? Hello? If you cannot, please say something.
I think also Eman raised the hand.
Maybe, yeah. Eman, you can talk now. Okay.
Examples of parametric tests like t-test or ANOVA test.
Yes. And another one that you have in your table, I saw in your previous lecture, you saw a table. Okay, so t-test, ANOVA. What else you have in your list?
Linear regression.
Linear regression. Yes, I think those three and the variant of these three type of basic analysis are the most important parametric tests, right? And you will decide based on your variables characteristics and also based on your distribution, right? So this is a summary of the potential parametric test, right? So you have here the t-test and pair, the t-test pair, right? Depending if you have two independent groups or one match group. And then you have your ANOVA and repeat measurements as well, or the independent measurements. And for sure, the correlation that you can use Pearson's correlation to relate to continuous variables, right? And also linear regression. I think Eman is raising the hand. You wanna add something?
No, thank you. I didn't take it down.
Sorry, because I saw the pop-up of the hand, so I was thinking, okay. So for sure you can participate in any moment. So don't just, you can raise your hand and we can listen to you. Okay, so then this is the summary, let's say, And as you can see here, we will discuss this after in the third part of the discussion today. But for categorical variables, we can say like implicit, we don't have enough assumptions to set a parametric test. You will see after, but just for that, we have this hyphen here in the table. And this is kind of in discussion. Some books include some tests here, other books none. So, but you will see in the next section. Okay. So, and how about the non-parametrics test? Could you mention some of them, please?
Anyone? Anyone volunteer?
Any volunteer?
Hi, Anna here.
Hi.
Okay, hi Anna.
We have the Wilcoxon sign sum, Wilcoxon sign rank, Crystal Wallace.
Yes.
Yes.
So one question for you: what is the difference between the run sum and the sign rank?
So the Wilcoxon sign sum will be for non-paired data. For paired data.
Yes, this is sometimes this is a confusion, right? Because some books use also Matt Whitney names, right? So just for you to remember, when you have the Matt Whitney or Wilkinson run sum, right? Or the run sum, it's for unpaired, right? And then the sign rank or the Wilcoxon, the classic Wilcoxon, it's for paired data. So that just remember that. I can show you in the table here. Yes, here. So as you can see here, for the unpaired data, you have Matt Whitney or rank sum or Wilcoxon rank sum, right? But for paired data, you have the t-test pair or the Wilcoxon, but signed rank. So this is kind of confusion, right? But just you can remember this table and you will be fine. Then you have the Kruskal-Wallis, you have Friedman's ANOVA, right? You have the Spearman correlation. You have other types of regression. One could be logistic, but you have others as well. And then for categorical variables, you have the chi-square and the Fisher-Exact with difference between them. You will see in a minute. But yes, the point is like, we can learn this using a parallel approach, right? So if you learn one here in one scenario, you can learn as well which one is the complement in the non-parametric profile, right? So then you can select based on your scenario. That is the idea, right? And the process of interpretation for both will be similar, because at the end you will do hypothesis testing, you will try to reject your null, you will interpret the p-value, and you will, as I mentioned, you will measure a point estimate, your interval estimate, and your p-value, right, to raise your conclusion. Okay, so then I remember one part in the case that Dr. Wang was thinking, seeing this stadium. By the way, it's a really good view. I would like to have this view in my work. So he's thinking which one will be the options and what is the potential problem. So if you can give me some ideas that you have from this discussion that Professor Wang is doing by himself. So anyone can help me?
Anyone?
Yeah.
If not, maybe Jason said you cannot talk. You didn't talk today, right?
Yeah, thanks. Actually, Dr. Wang has several choices. Actually, there are 3 choices, but either way will make them lose the chance to adjust for covariates or to increase the complexity of the test. One of the choices is to just use a non-parametric test like my Whitney test, which won't enable them to adjust for the covariates, especially for age, which they think that it is a potential confounder. And the second way is to categorize dependent variable and then use the categorical test like chi-square or Fisher's exact. But in this way, they could neither adjust the covariates. And the third way is to use a more complicated test, which I heard of this for the first time was CMH. Yes.
Yes.
But it's
yes.
quite complicated and like confusing.
Yeah, we'll talk about it in a minute as well. But yes, perfect. That's the main concerns of Professor Wang and the potential options. So what do you think about that transformation to use a log transformation or any other type of transformation?
Actually, in the forum, I raised the fourth, use a log transformation, and it is quite like attractive option. Like we can transform it maybe to a near normal distribution so that we can use a parametric test, and also it makes us able to adjust for covariates. But the problem here comes like the interpretability will decrease, and we need to back transform the data, which will be difficult to interpret. And a second problem is that the HAM-D, which is a rating scale and is considered originally as a ordinal data, and should we use it as continuous data? It is another debate.
Yes, that's perfect. Yes, that will create a problem of interpretability as well. Yes. So as you can see in statistics, when you are doing your own research, always is a trade-off between feasibility and validity, between conservative approaches and more power approaches or with more risk, right? So at the end, the point here for everyone to have in mind is like, it's not the best, it's not that one solution. It's not like you can pick one and this is the perfect one. Always you will lose something and gain something, right? So this is the thing that you need to be aware of. And also in your studies and when you are reading the papers as well from your critical thinking, right? Okay, so then thank you so much. Wonderful participation. So then the point that Professor Wang is saying is like, okay, I can lose information, I can lose power, how I will control my covariates, right? Maybe now my result will change and I need to change all my conclusion, all my discussion, you know, it's like you will restart again the paper as well. So sometimes happen, yeah, could be. But my question now for you is, if you are in that position, right, you think that in that moment, because you already finished the study, you have your protocol approved in IRB, so you can change your method of analysis now? What do you think? Do you think it's totally fine? You need to disclosure something? What do you think?
Anyone?
Yes.
Can I answer?
Yes.
Thank you. I think changing the analysis way at this time would let the trial be as an exploratory one, and that should be announced because choosing the statistical analysis test should be at the beginning while designing for the study. Doing that after the results are released, it should be announced and it will take the quality of the study down, I think so.
Yes, that is you know, from the ethic perspective, it's totally fine as you mentioned. You need to disclose that and to say this is a post hoc or not a predefined analysis, and then it's fine. You can do that, right? But you have to be transparent. That is my point, that you need to be aware as well, because what's happened when you send a RCT to a reviewer, to a good journal, especially a high impact journal, they request you your protocol, right? They request your current IRB protocol, and they check what you said before, right? I will use this and this, and to use the outcome in this way. So at the end, you need to be totally transparent. So the short answer will be, it's possible, we can change the method, but we need to declare that and to put a statement about that. Okay, so then, okay, so we already discussed about the potential solutions, right? Is anyone want to add one option, an extra option, not just the Matt Whitney or the categorization or the use of CMA? Anyone have another idea?
Hello, can you hear me?
Yes, yes.
Oh, okay. I was wondering if we could actually defend the use of a parametric test, because we know that this particular Dr. Wang, he sent the study with a parametric test, and they considered that wasn't the most appropriate since the distribution wasn't normal. But we also learned that the parametric test can be used in non-normal distributions when the size of the sample is big enough. So there would be like any way to defend the use of that parametric test?
Yes, yes. I mean, it's possible. Yeah. Why? Because do you have the idea of the central limit theory, right? So could you defend like potentially will be enough the sample size? But remember, like, I mean, this is a little more advanced. You will review in the future modules, right? But when you are testing the assumptions for a linear regression, the normality that you are looking for is the normality of the residuals, right? Not necessarily the normality of all the outcome. So you will see that in the future models. So yes, it's possible. That's one of the potential ideas, but it's kind of risky because you know that some reviewers will be more conservative. Probably they are like I don't know, the statistician who reviewed it, it's more conservative. And if they will make a claim in the research community, right? They want to be sure, right? So the point is like, at the end, it's possible, but depends too much on the decision of the reviewer. So let's say that will be a little risky and he can lose the potential acceptance, right? But
Okay.
it's totally fine.
Okay,
You can,
thank you very much. Thank you very much.
Yeah.
I have
another
respect.
Yeah.
In this study, I saw that Dr. Wang has two mistakes. One of them was to try to apply a parametric test in a skewed database. I think that he would try to apply some other kind of test, and another one is because of covariates. I think that if he in the randomization process, I think that he will stratify the people and not after that. And
Yes.
these two mistakes, I think that raised a lot of mistakes in the post-planet after that he submitted his paper. I don't know if you agree with me, but
Yes.
Always we have learned here, when you submit when you do a protocol, we do a pre-planned analysis of what we are planning to do, but after we apply the statistical test, I think that he has to analyze his database to see if it's normal or not normal to apply the specific test, and he applied in a wrong way. I don't know if I'm clear for you.
Yes. Let's discuss that second thought, because you know, in an ideal world we try to be with a 100% validity and to use all the background data, right, to design the best study, right? But let's put in the position of him as well. Like sometimes the best design is not feasible. So let's say that the grant that he applied is not too big, so you need resources to do a more complex sampling and more complex randomization, right? So, and remember, like, he is starting this process of the clinical research to probably do a confirmatory study after, right? So let's say that this is a preliminary or phase 2 study. So at the end, I totally agree with you. That will be the perfect solution. And for sure, if he wanna scale to the next level of the RCTs, he will take for sure this take into account, right? To do a stratification by age or even by depression severity, right? But yeah, I totally agree, and it's perfect that you realize that, because that is the thinking that we need here. But this is dependent of the scenario. So let's say that we are in a scenario of a phase 2 study, gathering some preliminary evidence. But yeah, perfect. Okay. So then, okay, so this is one option. So okay, we have so far, we can defend the parametric test. We can do a non-parametric and accept the non-normal distribution. We can categorize. We can use this approach to stratify, right, using the CMH. And what do you think? There is another option? Do you think we can use another test? Oh, I mean, also the potential transformation. This is another option, but we already mentioned that could be non-appropriate. And another one, do you have another idea?
Anyone?
No? Okay. So it's fine because we mentioned the most. Okay. Yeah.
Hi. Hello.
Can I talk?
Yes,
okay?
sure.
I usually thought that we can transform the data for binary and try to use logistical regression, but I'm not sure if this is the best option because, for example, we know we have different types of research questions. We have comparison, we have associations, we have predictions, and for each one of these, we have statistical tests specific for each one, and I don't know if it implies something about it. You know, I really don't know.
Yes, I think it's another option to use logistic regression, but at the end, it's together with the option to do a categorical data analysis, right? To categorize and to explore. You could explore using chi-square, Fisher, or do a logistic regression and to calculate the odds ratio. So I think it's fine. We will see in the second section about that. But yes, for sure you can use logistic regression, but you need to categorize first, right?
Thank you very much.
Yeah, I heard another one to saying something, another colleague as well.
I think that all depends on the variable that he wants to analyze. If he wants continuous, or if he wants categorical, or if he wants to stratify with covariates. But one thing is right. I think that he has to do a non-parametric test in here, because doing the parametric, it was wrong. So I think that we have to see what variable he wants to analyze. And there is no correct answer here. I think that even choice that he's making has some advantage and some drawbacks. And so if you dichotomize, it's better for you to understand. But you have a lot of you lost information and you lost power of your study. So
yeah,
it depends what he's trying to show. I think that, in my opinion, after reading the case and studying, I think that the better for him thinking about covariate age is very important in this disease. I think that the Cochrane-Mantel-Hansel, I think that's right, that's the better test, but I know that it has some disadvantages too.
Yes. Okay. So I think we have all the, let's say, possibilities. So now let's organize our ideas, how to decide. And I like that you mentioned the point that depends on your variables. And that is the first idea, right? So to start thinking, you need to identify the type of variables, because we already know that it's a non-normal, or we need to understand the variables. So for instance, if I just ask to you really quick, which one, for instance, the depression scale, post, pre, age, this group, allocation, which type of variable will be? For instance, this depression, what type of variable you think will be?
Categorical.
Sorry?
Categorical.
Yeah, I mean, could be ordinal, right? Or continuous, because there is a debate between them.
Oh,
right?
sorry. It's ordinal, okay.
in the depression scales, as well in pain and in other type of neurological scales, sometimes you can argue like it's a continuous, and sometimes you can argue that it's a ordinal, and there is a debate as one of your colleagues mentioned as well in the previous participation. But yes, but it's important to know, like, we can use it as a numerical variable. That is the point, right? You can justify that use. Age, for sure, it's a continuous variable, right? And this is categorical, right? So we are agreeing on that. So you need first to define this, right? Even though you have, I don't know, 20 or 100 variables, you need to know which one, the classification of each one. That is a good exercise for you in your studies as well, or in your group project. So then, okay, so we have kind of this classification, right? And remember that age is the important covariate, right? And this, we can assume that it's continuous, could be ordinal, I know. But then, you know, like in the PICO question, we have the idea of difference, right? So you are, at the end, are creating another variable, subtracting the baseline and the after treatment, right? So this one is the most important at the end in the initial analysis of the study, right? So then, okay, so we have this type of variables. So let's select the initial test, right? So we know that it's non-normal, so we can focus on non-parametric, right? And then here, which one is the obvious option? I think you already mentioned that, is the Matt Whitney, right? That would be the initial option. But as you mentioned already, we are comparing ranks. It's not all the data points. And then, yes, you will have, you will lose power and information, right? So that will be one option. So then the point is, you can modify the variable classification to accommodate the statistical test, because normally we are saying you need to identify which variable you have, and then you need to select your test. But my question for you is, it's fine that you do the opposite, like you change your variable in order to accommodate a statistical test? What do you think? Anyone?
I think we can.
Sorry, who mentioned that?
This is Iman, and I think we can revise a variable from, for example, from continuous to have it as an ordinal or categorical to fit in the statistical test.
Yes. Yeah, I think it's possible. Yeah, totally possible and fine. But you need to justify and to be really careful to select your threshold or your cutoff, right? Because what is the problem here? Like, depend on your cutoff, you will divide your data maybe in a symmetrical position as well, and you can benefit one category versus the other. So you need to be really careful and to read up a lot of papers before to see if it's possible, right? If someone did before, if you have a plausibility from a clinical perspective, right? So in this case, using the depression scale, so by default, when the people create these scales, they create categories, right? Mild, moderate, and severe, and they try to do this type of cutoffs to define. And it's really common this in the neuropsychological field as well, right? So I think in this case, we can justify for sure, and to define a specific number of points to say responders and non-responders, right? It's possible as well. But the message for you is, it's possible, but you need to be careful and you need to justify, and it's important to justify this in your paper, in your protocol, right? With reference or with a plausible explanation. Yes, okay. So then now we have new variables. We have, for instance, severity of depression, responder versus non-responder. We can categorize also the age, right? Adolescent versus non-adolescent, for instance, could be another option. And then this categorization ideally should be done in your protocol, right? So that is a really important point as well. But if you design this a posteriori, you need, again, as you did in the new selection of tests, remember that we discussed minutes ago, you need also to state this in your paper, because it's an important departure from your protocol in an RCT. So you need to mention, especially if you plan to change your main outcome. That will be the big problem, right? Because initially our main outcome was the difference in the depression scale, and now we are changing to responder versus non-responder. So we need to be really careful on that. And let's say one good idea for you that writing the group projects or in your grants in the near future, to have a plan B, right? Especially for NIH, when we apply for grants, there is a section of unexpected results or potential pitfalls in your hypothesis. So they give us a lot of points if you can have plan Bs, and that even though negative results or unexpected results will be important for the field, and they do a writing of this section. So that the home message will be careful. If you have a continuous main outcome, be careful to think before if it would be a good idea to have sort of a secondary outcome, category secondary outcome, or to use this stratified design since the beginning if you identify important covariate. You see, so that is important for you learning as doing the writing of grants, right? Okay, so now we have a new list with new categorical variables, and at the end we have a new selection process, right? With this section here, as one mentioned before, logistic regression or Fisher or chi-square, depends on our normal approximation. Okay, so then we ended up with these two big blocks, right? That one is to use a raw non-parametric test using just the difference between group using McWhitney, or to start thinking as a categorical data, do the transformation, and to use odds ratios using a logistic regression, or to use this Cochrane-Mantel-Hassel test to adjust, in quotation marks, because it's not really an adjustment, it's a stratification of the odds ratio, right? So we agree that those will be the most important. So now my question for you is, okay, so we decide more or less like this one is the best approach, that you will lose less, you will have problems anyway because you are changing your main outcome, but maybe it's a more robust, right? And then what is the odds ratio? Do you have an idea? Because we were thinking about that as a potential solution. Anyone can give us an example of odds ratio or a basic definition?
Hello?
Yes?
Hi, this is Hans. So maybe odds ratio to be defined as a kind of a measure of association between our intervention and our outcomes?
Yes. It's a measure of association. And what tells you? Like risk, a probability, I don't know. What do you think?
Well, it could be like as far as I know, if your numbers, for example, above 1, you can say that is more probability to happen, right? If below 1 is less probability.
Yes. I think there is a big discussion about the odds ratio, because it's not really a probability, it's not really a risk. It's kind of a odds, right? The definition is odds. You have more odds or less odds. And the odds, it's kind of, yes, it's a complex definition because it's a relative measure. But let's say that it's a possibility, or like if the event will happen or not. That is the idea, right? Okay, so anyone want to add something? I think I heard something. No, right? Okay. So then, yeah, it's perfect. It's a measure of association, giving us the information if some event will happen or not in a specific group, right? So what is important now, because in order to understand our second section, our second option, we need to create this table, right? A 2x2 table. So we have the treatment, that is the exercise. We have here the usual care, and we have now our new variable responders and non-responders, right? So then we can create the odds ratio measurement using a logistic regression, right? And how? Using this cross multiplication, right? That is the simple one. Let's, for now, let's keep this idea, but you will receive a better explanation in the module 5 in observational studies. But yes, it's like a multiplication, right? And the idea to see is if the treatment has more odds of response versus the odds in the usual care. That is the idea. And as Hans mentioned, you have the cutoff. Let me show you this, between 0 and the infinite, and the cutoff of 1, right? Meaning, if you have 1, you have a similar possibility, and if you have less than 1 or near to 0, you have a small possibility of that event, and if you have more than 1, you have large possibility, right? So just for you to remember how you can interpret this. So someone can give me an interpretation. If you have an odds ratio of 0.8, what you will say?
Less harm or protective.
Yes, it's protective. But remember, like, to understand the odds ratios, you need to use that 1 as a reference. I think Eman mentioned, when I mentioned something. Yep.
Yeah, I was about to answer it. I mean, its outcome would be, for example, 20% less likely to happen.
Yes, that is the point, and I want to go there. Because you need to use 1 as a reference. Meaning, if you have 0.8, you need to subtract from 1, so you have 20. So at the end, you can say you have 20% of possibility, right, that this event won't happen, right, because you are less than 1. And if you have here the odds ratio of 1.2, you have 20% that this 20% of possibility that this event will happen in the future in this group, or it's happened now. But the point is, like, you need to use 1 as a reference. And the last question for you, if you have 2.50, how you interpreted this in percentage of possibility?
It would be 2.5-fold possible to happen more likely.
Yes, this is one option, but if you use the percentage,
150% more likely to happen?
yes, 150%, yes, of chance or of possibility, right? To be honest, it's odds. It's 150% of odds of the event, but the odds is kind of weird definition. So let's say possibility. Okay, so now this is important. Why? Because one option is to have an odds ratio saying the responders in 2 groups, right? The odds ratio of respond to the treatment in depression, the depression response in both groups, right? But the point is now that we need to stratify by age, because we know that age could be an important confounder, right? An important variable to adjust. So this is the Cochran-Mantel and Hassel, meaning you divide your table, say this table, and you create 2 tables. So you create one table just using adolescents, and other table just using non-adolescents, your other category. So you will end up with this. You will have a table with adolescents and non-adolescents, and you will have A, B, C, D as well. And you can do the cross multiplication and to create 1 odds ratio for adolescents and to create 1 odds ratio for non-adolescents. And then using the CMH formula, you can combine these 2 and to test if they are similar. And you will have a just odds ratio by the age category. So that is the idea. I don't know if you understand. We will see in the few minutes a practical example of this.
I have a question here.
Yes. Yes.
There is, you said risk. I want to know risk of what? Risk of not being possible to happen, or risk of what?
Of happen, sorry? Can you repeat, please?
Yeah. In the calculation, the previous page, I think, the previous page, there is a risk different. Risk different. Yeah. I want to know what is yeah, here. What is the meaning of risk here? Risk of not being possible to be happen, or
yes, that is a good point. I wanna check the odds ratio first, but yes, let's so the risk, it's the risk of the event, that the event happened. But in this case, we can use risk because it's a prospective study, right? But the point is, like, if you will generate relative risk or risk difference, you can use a logistic regression. So that is the only problem to calculate risks directly. So for that people use more odds ratio, because you can use logistic regression that give to you by default odds ratios, right? So the point here is, like, the risk, it's a measurement of possibility, in this case of probability, that something happen, that an event happens. So to understand this, you need to define two things. The first one is which one is your group, the reference group, in this case is our treatment, and then to define which one is your event, right? Because if we define treatment as my reference group and respond as my event, the risk will be the risk to have this response, you see? But imagine that we decide non-response as our event, right? Does this risk, relative risk or risk difference, will be the risk or the probability of non-responders. You understand more or less? The risk is of the event that you define.
Yes.
Or the probability. In this case, we can say probability, because at the end it's a probability, not like here, like it's a odds, or it's kind of possibility, let's say. Okay, so then that is the potential solution for Professor Wang, right? So he can report the odds ratio, stratify, and then combine using weights of adolescents and not adolescent, and this can give us the information if you have more responders in your treatment group. You see? So anyone have another question about these two approaches, to use odds ratio or Cochrane-Mantel-Hassel?
Can I ask a question?
Sure.
Would the sample size affect the result generated by the CMH test?
Yes, because at the end you are dividing your approximation, right? Your calculation. So you will lose power for sure, but it will be the most near to your estimate using linear regression adjusted by age. So there will be kind of similar, or at least they will go to the same direction, right? But yes, the sample size will give us not enough power probably to detect the real effect. That is true. But just for you to understand, like, we are trying to replicate in some way this linear regression adjusted by age, right? So this could be another way to see this option. And anyone else have another question?
Yes, please. I'd like to ask, is Cochrane-Mantel test equivalent to chi-square followed by post-hoc?
Sorry?
Because
could you repeat, please?
I have read that chi-square would show that there is a difference, but wouldn't show which category is responsible if we have subgroups inside, or we suspect the covariates. So we do repeated post-hoc tests to check the group which is responsible for the difference, or which two groups are showing the difference in the results. So I can see here Cochrane-Mantel adjusting for the covariate from the beginning of running the test. So this is equivalent to chi-square followed by post-hoc, right?
Yes, could be another option, but I mean, they are similar in nature, but the point is, like, this Cochrane-Mantel-Hassel give us different weight. So it's not like a arithmetical combination. Let's say that it's a ponderate combination. So at the end, this odds ratio, this new odds ratio, is taking into account the variability in this table and the variability in this other table, and the sample size for sure, because maybe you have more adolescents in your group, right? So this odds ratio here will have more weight. So at the end, it's not the same that to do a post hoc analysis after the chi-square or other type of categorical analysis. It's a different concept. So you are stratifying and combining this stratification in a one unique odds ratio. You see?
Perfect.
I know it was clear.
Thank you.
Yeah. And for sure you have some advantage and disadvantage, right? But in this case, could be one of the best options to be transparent. And to be honest, this approach is conservative, right? Because if you have some people in this group, right, that is changing like 1 point in the depression scale, but they couldn't be classified as responders because they are just 1 point below your threshold, right? You lose that observation as a success, right? So at the end, if you use this approach and you are still having an odds ratio positive or significant, let's say, you have even a better justification of your results because you are using a really conservative approach, losing power and losing information, right? But I understand your point, like in this stage of the research with a small sample size, just exploring the results, maybe we change the results of Professor Wang. But okay, so that is the point. So any other question about this?
I have one more question.
Sure.
While I was reading the CMH test, I came across this term called the Simpson's paradox, and I was wondering if you could explain it a little bit more.
The paradox of what?
The Simpson's paradox.
Oh yes, the Simpson paradox. Yeah, this is a nice example. Yeah. So what's happened? So if you have, I mean, maybe I can show you during the practicum because we will do this in the data with an example that I sent to you. But it's like that. If you have a odds ratio, for instance, of all these two groups, right? Imagine the odds ratio is 1.8, right? The total one, the crude, the raw one odds ratio. But if you calculate the odds ratio here and the odds ratio here, imagine that you have here 1.2 and here, I don't know, 0.5, you see? So at the end, if you sum up, these two are not the same as the total. That is the paradox. Because the intuitive, you think that will be, if you sum up, you will have the total odds ratio, right? Or the total effect. But it's not like that. Why? Because you have different variability in each stratum. So you need to weigh each stratum in order to get that total odds ratio. So that is the paradox, but you will see in the example, right? I don't know if it was clear, more or less.
Yes, thank you.
Okay, so I don't know, let me see the time. Okay, so that was the case. So now I think we explore all the options. We decide like the categorical transformation, and this approach of odds ratio will be the best option, maybe, but potentially we will change the results of Professor Wang. That is the idea. But let's see, we don't have the data, right? So we can really be sure. Okay, so now let's do a practicum of categorical data analysis. I don't know if everyone got the data set. Keiko, can you confirm that you receive it?
Oh, you can. Maybe we can download it.
Yes, please. If maybe we can give us like 2-3 minutes to, if you can open your data, upload the data set, because the idea in these minutes that we have is to run the analysis, to explain the outputs, to be together and to because sometimes we don't have time during the lecture, the Thursday lecture. So please, if you can upload now your data set.
The data set will be the same data set of the previous week, or where?
No, it's a new one that probably Alma.
It's already sent.
Oh,
They sent
really?
it already.
Where she sent it?
In Google Classroom. In the optional lecture, in the classroom, Google Classroom.
Well, I cannot find your dataset in the Google.
It's there in Google Classroom. It's there.
Okay.
It's sent after the live lecture.
If you cannot find, maybe I can send it to you. Okay.
Maybe you can put it
The
in
live
the
lecture,
chat.
under the live lecture, the optional lecture data set.
Can you? I have the
Do you have
data.
it?
I have one, but I'm not sure. Oh, okay. Maybe everyone can find it.
I don't know, or maybe I can
Is
send to
the one that
you.
you put in the chat? That Rosalma Eusebio put in the chat. That one is the correct one?
Hi, everyone. Hi, everyone. Can you find it? Can you find the data?
Is the one in the chat?
Okay, yes. Maybe if you cannot find, could you please open the link in the chat? Does it work?
Okay, so we are ready?
I think so. Is it okay for everyone? If you cannot find, please email to me. Maybe I can send back to you. Okay? Okay, maybe we can go ahead.
Okay, so then the idea of this last part is to explore a similar example that Professor Wang, but let's imagine that we already have the categorical data, the two categories on each, the groups as a predictor and also as a, let's say, dependent and dependent variable are categories, right? That is the main assumption that we need. And okay, so let me just give you a brief background of this data set. So we did a survey in chronic pain patients in the lab with the idea to assess if the underrepresented population, right, defined as economic and stratum, education, and also ethnic minority, right, are associated to the less participation in our trials, right? So the idea is to see if you are underrepresented, your possibilities or chances to participate in a trial. See? So we have, let me show you the data set. So we have three outcomes here, three variables. Underrepresented, I know, can you see my Excel? Yes, right? Yes?
Yes,
okay.
we can see it.
So then we have underrepresented, and 0 is no underrepresented, and 1 is underrepresented, and participation is the participation in the trials, right? It's a survey, so we asked them in the past 6 months if you participate in one RCT in our records. Also, we can confirm, but the point is like 1 is yes if you participate, and 0 is no. And then we have this covariate similar to Professor Wang, saying if you are on top of this underrepresented definition, if you are a woman or not. 1 is yes and 0 is no. Okay, so then let's go to Stata here and let's export the data first. As you know, we can use 2 different approaches to export, right? Because we have a really small, I mean, not too much variables, we can just copy and paste. It's really simple. Or you can, in order to avoid problems, you can go here. Let me show you. I think you already know that. but import data, Excel, right? You choose your Excel file, and then you choose the worksheet that you want to export, and it's important to mark this, right? Important first row as variable name. Okay, so everyone already knows that, right? It's fine that this step?
Yes.
Yes, okay. I don't know why they have these lines here. Can you see these lines? This red line?
Yes.
Yes.
So here. Yeah, let me see. How can I move this? Eraser. Okay.
Maybe
So,
open the pen. Yeah.
so weird. Okay. Okay,
Sorry,
so
doctor,
then.
what is the meaning of underrepresented? Can you explain again for me, please?
Yes, yes. The underrepresented is the category that you have, or you have three definitions. If you have less income, right, in your family, in your household, if you are a minority, like for instance Latino or African American population, something like that, and if you have less education, let's say high school or less. So these three characteristics define in this data set if you are or not underrepresented population in US. It's clear now?
Okay. Yes,
okay.
If yes, 1, if 0, if not, 0.
Yes, if it's 1, it's like you are underrepresented.
Yeah.
And if it's 0, it's no. Okay. So then we have here our three variables in your data editor. So I hope some of you are doing the same at the same time. So then the first step for sure is to tabulate our variables to understand the distribution, right? Or at least the frequency in this case. So as you can see here, I tabulate underrepresented, and we have 116 zeros, right? And 74 underrepresented, right? It's clear that? And then let's see the participation variable, and we have as well 107 zero, meaning no participation in the past 6 months, and 83 participation. And then just to see the other one, we have as well a frequency of the three variables. So it's always important to use your descriptive statistics to understand the percentage, the frequency of all of them, right? Okay, so then for sure, I don't like to have this 0 and 1 could be confusing, so let's create labels. You already know how to create labels, but let me show you the syntax again. So it's like that. You use label, define the name of your label, right? And the meaning of 0 and 1 in quotation marks, right? In this case, 0 is non-underrepresented and 1 is underrepresented. So I just put label define, the name of the label, 0 and 1. So then I need to assign the label to one variable. So then it's label values. This is to assign, and I put the name of the variable and then the name of the label, right? And then you will have the label like this. Instead to have 0 and 1, you will have non-underrepresented and underrepresented. I will share with you at the end of the session all the commands so you can use in the future, but the syntax is similar for any type of variable, right? So let me just do really quick the others to have the names as well. This is for participation. And this is again assign the, I'm just doing one by one so you can see. And to assign the label for women. So then, oh, it's the opposite. First should be the name of the variable. Okay, so now you can see in data editor that you have the three variables with all that labels, right? So now it's easier to interpret, right? Okay, so then we have the hypothesis to see if your underrepresented are associated to less participation, right? So we are clear here. I don't know if it's too small. Let me increase the font 1 second. Can you see better now? I think now
Yes.
looks.
Yes, now
okay.
it's better.
Okay, yeah. So then the first step, right, is to create our 2x2 table. So how you create the 2x2 table? Just tab and underrepresented and participation, right? Maybe we can even move participation first because this is our main outcome, right? We want to see if the underrepresented are associated with the participation, right? So then let me press this, and this is our 2x2 table, meaning you have a non-underrepresented, right? 116, underrepresented 74, and participation and no participation, participation and no participation, and then the frequency between each category. So we are fine on that, right? So then what's happened? To apply the chi-square, you need to compare your observed cells versus your expected cells. Do you remember that from the theory, right? So let's see how look like our expected cells. Oh, sorry. Expected. So this is our expected table, meaning this is our observed values, right? And this is the expected based on our proportion here. So you expect to have 65, 41, 50 something, and 32 something, right? Everyone is clear with this concept of the expected and non-expected, or you want a better explanation in the PowerPoint? Just let me know to okay.
Explanation.
Yes, Alberto? Yeah, explanation. Okay, great. So
Sorry, I
let me
didn't. Yeah, I didn't catch very well the difference between the expected and the frequency observed. Sorry.
Okay, let me show you here. I have an example. Yes, yes. So let me show you here. Okay. So can you see here this table? Like we have 200 patients, right? Doesn't matter that the meaning of these two. Don't worry. So yes, you have 200 patients, and you have 100 in each group, right? And then you have here 50 in this category and 150 in this category, meaning you have a proportion here, right? So my question for you is, which percentage is 50? Which percentage of 200 is 50? Can you answer that? Which percentage
100.
of 200 is 50? Sorry? No, it's the opposite. If 200 is
25%.
Exactly, 25%. And 150,
25%.
75%. 75, yes. So you have this fixed column, right? Because you already know that this. So then you can extrapolate these numbers because you know that this one is 50, 25, and this one is 75. And you know that this is 50 and 50, right? So this should be 25, 25, and 75, 75. You see? So this is your expected based on your proportion in the, let's say, in the margins. You see? You understand more or less now? Because this is fixed from your population, right? How many you have in each group and how many you have with the events. And then you can calculate the expected values based on these proportions. Let me put another example. Imagine that you have here 200 again, 100, 100, and you have here, I don't know, 25, and here 175. You see, again, you can calculate what is the percentage of 200, it's 25, and what is the percentage of 200, it's 175, right? And then you can use that numbers to fill out all these cells. You understand that part?
Mm-hmm. Yes.
Alberto?
So if I understood correctly, basically what it allows is to give us 1%, And later in further studies, or in case that we have a bigger sample, we can estimate what is the estimated percentage of people that is going to be assigned to each square.
Yes. Yes.
Okay. Okay.
Yes.
Thank you very much.
Because
very
remember, like you, in your null hypothesis, you are saying that the two groups are equal. So you can always split in 50-50 because you are assuming that in your null hypothesis, right? So yes,
okay.
that is.
Thank you very much. Okay. Thank you very much.
Great. So then we come back here, and then this is the expected based on the proportion. That doesn't matter here, the proportion we need to calculate and state that, do that for us. But the point is like the chi-square, right? And in some way Fisher as well will compare this observed value versus the expected value. And then for each cell, these 4 cells, let me show you the formula if you want to be even more clear. It's the observed value minus the expected value square divided by the expected. This is the formula that chi-square is using for you to calculate your chi-square statistic, right? And then you can use the chi-square statistic to test your critical value and to see if it's smaller or higher than 0.05. That is the idea. See? So let me now do the chi-square. So as you can see here, it's the same table, but they already calculate this observed minus expected, square, divide expected. So we don't need to do manually. You can do if you want. It's possible. But then automatically they calculate 33 chi-square statistic. And remember, like in the chi-square distribution, your critical value is 3.84, meaning if you have higher value than 0.84, you will be in this extreme portion of the distribution, meaning less than 0.05, right? That is the idea. So then we have 33.6, certainly it's higher than 3.84, so it's significant, as you can see here, 0.000, even it's undetermined. You see? So that is the chi-square. You have any question about this?
Yeah, 3.84, is it similar to the p-value in significance? We can use it but in chi-square, or
yeah,
what is the story?
Yes, this is a different point, but okay, let's do that. I have here actually, just for you to remember. So you need to remember 2 things. The first one is the critical values, and the second one is your p-value. There are different points. So when you have a normal distribution, your critical value, let me just put this as a presentation so you can see better. When you have a normal distribution here, right, you know that you can identify the probability under the curve, right? Or the quantity of data under the curve. Okay. So then when you transform this to a standard deviations or your C statistic, right? A C statistic, you will have a critical value of 1.96. So meaning, if you have a C higher than 1.96, you will have your value here in this area. So the critical value give to you the threshold if you will have a p-value less than 0.05. But in chi-square, you use the chi-square distribution. That at the end is just the square of the C. So you will have 1.96 squared is 3.84. So for that, your critical value is 3.84, right? But remember, the critical value is another way to see, like you have, let's say that you are in this extreme area of the curve, right? And just if you want to go, yeah, sorry, you want to say something?
Yeah, if Z more than 1.96 or chi-square more than 3.84, that means we are away from the mean, this normal distribution, and the data is not significant or
no, the data is
or,
significant. It's significant because remember, like you want to be in the extremes. You want to be a rare event to be, let's say, not explained by chance. You see? So you want to be in the extremes. So if you have higher than these values, than these critical values, you are here. Therefore, you are significant. That is the concept that you will use for a lot of distributions. For instance, the C is using for the C and the T is using for t-test. This X square or chi square is using for chi square. The F distribution is using for ANOVA. But at the end, always you have a critical value, and you have here a area, extreme area that you want to be there. Okay, so I hope this is clear now.
Clear, thank you.
And then
excuse me.
Yes. Yep.
Sorry, Kevin. If the chi-square is less than 1.96, or the chi is more than 3.84, less than that, that means it's significant results. Because if it's more than this, it's not significant. So less than this, it means significant. So I can take
no, it's the opposite. If it's higher than this, it's significant. You expect to have higher value, because if you have higher, let's check here. If you have here, for instance, 1.96, that is approximate 2. If you have 2.1, you have 3, you are in the extreme, right? So you expect to have higher value, you see, to be significant. Okay.
Okay.
So now I hope it's clear. And then just for you to remember, this chi-square distribution is just using 1 degree of freedom. Meaning, if you know just one value, you will know all the table because the margins are fixed, as we saw in the example of the expected value. You see? So at the end, if you know just one, if I give you 46, you can calculate the other 3. For that, you just use 1 degree of freedom. Okay? So then you have this piece of code here to create your chi-square. And what is your interpretation of this table? Could you give me an interpretation, please?
Let me try.
Okay, that's fine.
For not participated, the observed value was 46, but expected is 65.
Yeah.
I don't know if okay, yeah, it's above than 33. That means it's significant.
It's significant, yeah. But remember, like our hypothesis is like the underrepresented people versus the non-underrepresented participate more or less. So my hypothesis is like the underrepresented participate less, right? So the cell that we wanna see is this one, because the people underrepresented participate less. And certainly they are participating less. Look, the underrepresented non-participation is 61, and the underrepresented that which participate is just 13, meaning most of the people in the underrepresented category didn't participate in our trials. So we are missing this population in the RCTs. That is an important thing as well in terms of external validity, right? So that is the conclusion. So we can say that underrepresented is associated to the participation. You see, with a chi-square of 33 and a p-value significant, right? You understand that?
Yes, yes.
Okay, so the underrepresented is associated to the participation. That will be the short answer. Okay, so then let me now give to you the Fisher exact, right? So as you can see here, at the end, we will have similar result. Why? Because all of our expected values are higher than 5, right? So we have enough sample size that this approximation with chi-square is similar to the exact p-value of the Fisher exact. You see? So at the end, in this example, they are kind of similar because the p-value are almost the same, right? Probably there are some decimals in difference, but are undetermined, right? Okay, so just you need to add exact from a practical perspective, you just need to add exact in your code, and that's it, right? So the question now is how we can define the odds ratio. That is the point. I think it's not in the let's say in the program itself in the past assignment, that I want to share with you because to complete the idea of Professor Wang. So you can do a CC, right, to create your 2x2 table to calculate your odds ratio here, in this case 0.14, with a confidence interval of 0.06 to 0.29. So please, someone can interpret this odds ratio here, please. Someone?
Hello?
Please challenge, please.
Hello?
Go ahead.
Yes, yes, go ahead.
Hi. So maybe you could say there's 86% of possibility that the event won't happen.
Yes, and in this case, what is our event?
The underrepresented people. So there's 86% of possibility that the underrepresented people won't participate in the studies.
Yes, exactly. That's the point. So at the end, if you are underrepresented, you have less chances to participate. You see? Because you have a 0.14 odds ratio or 86 percentage, right, of possibility to not participate. That is really high and was kind of really shocking for us because at the end in the RCTs you need to be in order to have external validity, you need to also have different type of population, right? So if systematically we are excluding the underrepresented people, right? So when we try to extrapolate our results, it's not valid, right? That is the point here. So then let's do now to finish.
Would you please repeat that part for the out radio, how to interpret the out radio?
Okay, sure. So to interpret the odds ratio, you have to define your event first. That is the first step, just like the practical step. Our event, it's no participation, right? Just keep that in mind, no participation. So then the odds ratio, it's the possibility, right, to one thing happen or not happen. In this case, that no participation in clinical trials, right? So if we have less than 1, meaning you have less possibility. The point is how much of this less possibility. And to calculate how much, you just need to subtract 1 minus 0.14. So you have 86 percentage of less possibility of your event, right? And the possibility in this case is of no participation, meaning your underrepresented people have 86 percentage of possibilities to not participate. You see? I don't know if now it's more clear. I know that sometimes it's kind of complex, but for sure this you will review in the Module 5 observational studies about odds ratio and relative risk, but just to give you the idea that Professor Wang did. So then, just to finish, how to do the famous CMH, you just put comma here, by, and the grouping variable, in this case, woman. You see? So then let's see what's happened if we add woman. So if we divide the tables, if we create one table for women and one table for men, and then in each table we calculate the odds ratio of each table, we will have 0.16 in men, underrepresented men, and 0.05 in underrepresented women. You see? With confidence interval without including the 1, so both are positive, are significant, right? Then what you can say just using these two numbers? What do you think?
That women has less possibility to be to participate in demands.
Yes. So even though if you are an underrepresented woman, you have even less possibilities to participate in the studies, right? So then the crude value is 0.14, like here, this is the crude, right? But the MH combined is 11, you see? Why? Because each odds ratio gives to you a different weight based on the variability in each table, the table for man and the table for woman. And then you have an adjusted odds ratio as we suggest to do to the case of Dr. Wang, right? And then what else gives to you this command of CMH test is the comparison between against 1, meaning if this odds ratio is significant or not, the combination after stratification or adjustment, let's say. And what you see here, it's 0.000, the p-value, right? So it's a totally significant, right? So again, as you can see, the commands are really simple. Yes, you need to practice the interpretation. But yes, if you have any other question about that, just let me know. Do you have any question about this last part? Just to be sure that everyone is on board.
So hello, Dr. Pacheco, question. So the command CC is used basically to, if we want to check always y-square or Fisher test, always we need to use this CC command, correct?
No, the CC is just for the odds ratio.
Only for odds ratio, okay.
Only for odds ratio, yeah. Okay. But for chi-square or Fisher, you just need to use TAP.
Okay, TAP is for
categorical. Yes, and always I like to use expected, because just to not forget that at the end, what are you doing is to comparing your observed minus your expected, right? So just for you to be aware of this kind of a black box that is happening behind all these numbers, right? To give you this number here. So yeah, as you can see, it's really simple. I will send to you all the commands here. Let me show you, so you can practice. And if you have any other questions, here you have all the commands that you can use to create the tables and to create the odds ratio and the CMH. But the most important thing is to interpret, right? What is telling you this chi-square, what is telling you this Fisher, and what is the meaning of this odds ratio. So, and just to finish, because one of you asked me about the logistic, right? So let's do really quick
Kevin,
the logistic.
Kevin, before we go, can I ask a small question about the table?
Sure.
Regarding the chi 2-1, which is the under the table. In the previous one, it was 33.6 more or less, but in MH chi 2-1, 23.6 is reduced. What does that mean?
Yes, that's a good point. Why? Because we are using a combined table. So what is happening? You have, let me show you again here. You have here two tables, right? So this chi-square is calculated at 33, is calculated using this table. But when you are dividing in two tables, you are giving different weights to this table and different weight to this table. So at the end, the sum to calculate the chi-square statistic, it's different. So you expect that you reduce the size, the value, because you are dividing the table. That is why. So it's totally expected. You mean this one, right?
Yes.
Yeah. Yes. But the point is like, they in this case, it's so strong, the effect for that didn't change. But what could happen for Professor Wang? Like if he used for the total and then divide by age, probably he lose the power. We don't know, right? That is the risk that he needs to decide, right? But yes, for sure. This should be different because you are using the stratification. Okay, so then just to finish, if we use the logistic as one of you said, the idea is to have an odds ratio as well, and you have 0.14, the same one, you see? So at the end are the same calculation, 0.14 here in the crude, here 0.14, And again, here 0.14. Maybe the confidence interval changed a little bit because they use a different way to calculate it, but for sure, all of them are significant. As you can see, don't include 1 here, don't include 1 here as well, and as well here. But the boundaries maybe are a little different, but it's the same at the end of the day, right? So yeah, as you can see, we can use, just to summarize, we can go from chi-square, Fisher exact, we can go to the odds ratio, the stratify odds ratio, or the logistic regression, and we ended up giving the same result, right? The same conclusion, the same interpretation. Like if you are underrepresented, you have less chance to participate in a clinical trial. And if you are underrepresented woman, you have even less chances compared to men. Okay, so I don't know if you have a final question, but I hope all of you enjoyed the lecture today. And for sure, if you have some, I don't know, question after, remember that we are doing a puzzle here. We are giving to you different pieces of information to create your big puzzle and to go, I like this pie, because at the end, you have things that you know, you have things that you know that you don't know, like maybe now, but we have a bunch of things that you don't know that you don't know, right? So the point here is to help to you to expand this puzzle and to expand this idea. And thank you so much. I hope you enjoy and we increase this pie together. And if you have any other question, just send me an email to this email there. I think you will have the PDF as well and the comments and the commands for Stata. And okay, so thank you so much. And thank you, Keiko, for all your help as well.
Thank you, Kevin, for your nice
Keiko, you're
and
muted.
wonderful lecture, Kevin. Thank you. It's really speaking. Thank you very much for
Thank you, Kevin.
Thank you.
Wonderful.
Thank you.